Morning everyone, I'm Mengchen from Jeremy Levis Group at the University of Pittsburgh. Here I'm presenting our research project of studying anisotropic superconductivity of nanowires at 110-oriented LaAlO3SrTiO3 heterointerface. This work is collaborated with Mengchen and Arandu's group at National University of Singapore. So recently, an unexpected conducting interface has been reported in 110-oriented LaAlO3SrTiO3 interface. It is unexpected because there is no polar discontinuity across the 110-oriented LaAlO3SrTiO3 interface, as we can see from this figure. For both sides of LaAlO3SrTiO3 in 110-oriented samples, one layer is +4 charged and the other layer is -4 charged. So there is no polar discontinuity across the interface. But compared to the regular 001-oriented LaAlO3SrTiO3, the STO side, each layer is charge neutral, and the LaO side, one layer is +1 charged, and the other layer is -1 charge. So across the interface, there is a polar discontinuity. But there is still a critical interface discovered in the 110 LaAlO3SrTiO3 interface, which is 4 in the cell. Above it, the interface is conducting. Below it, the interface is insulating. And also in this Nature Communication paper, anisotropic sheet resistance has been reported. And recently, superconductivity have also been reported in 110-oriented LaAlO3SrTiO3. So now, in this talk, we are interested to study the anisotropic superconductivity in 110-oriented lanthanum aluminate strontium titanate heterointerface. So to study this, we use our conductive AFM lithography technique to fabricate nanowires along the two different in-plane crystal orientations. We have the sample patterned by 16 electrodes forming a 30 micrometer canvases for the conductive AFM lithography. And we can create nanowires, which is similar to the 001 case. So this is animation showing how we make the nanowires. Basically, a positive biased tip, we move a positive biased tip to make one nanowire along the 001 direction and the other nanowire along the 1-10 direction. And after that, we will write 2 more nanowires serving as the voltage needed, measuring the 4-terminal voltage drop of the 2 nanowires. So here is the schematic of our device and measurement. So basically, the nanowire is 10 nanometer width for both directions, and the separation between the 2 electrodes are 6.5 micrometer for both directions. And we can source current between electrode 1 and 6 and measure the 4-terminal voltage drop along the 001 direction and also the 1-10 direction. And after that, we just cool down the sample to the base temperature, and first we didn't turn on the external magnetic field and just sweep the temperature. And then we can measure and plot the 4-terminal differential resistance as a function of temperature and the bias current. So here is the intensity plot, and here is the waterfall plot. So from the intensity plot, we can see the superconducting transition, and as this blue dashed line indicated, we can also plot out the 4-terminal differential resistance versus temperature near the zero bias. And from this data, we can see the superconducting transition is brought in the temperature window, and the critical temperature is around 150 milli-K. And then we can turn on the magnetic field and also sweep the temperature underneath under different external magnetic field. So the different color shows different magnetic field. We are taking this series of data and compare the 2 family of curves along along the 001 direction and one along the 1-10 direction. We can already see upper critical magnetic field difference for the 2 directions. So to study the magnetic field dependence more closely, we can fix the temperature at 70 milli-K and sweep the external magnetic field and measuring and plot the 4-terminal differential resistance. Here we plot it out as a function of the external magnetic field and also the bias current. So from the intensity graph, we can see the superconducting transition and also the upper critical field is different for the 2 directions. We can also study the superconductivity under different backgate voltage. So this 15 figures shows the how we turn the superconductivity using the backgate of the nanowires along the 1-10 direction. So in the beginning, when the backgate voltage is 0 volts and negative 0.1 volts, there is no superconductivity of the 1-10 nanowires. And if we keep applying more negative backgate voltage, the superconductivity shows up and becomes stronger and stronger. But when the backgate voltage is getting more negative, the superconductivity is getting suppressed and finally disappeared. And here we are plotting the normalized differential resistance. And also we can do this for the nanowires along the 001 direction. And in this case, first, even when the backgate voltage is 0 volts, there is already superconductive behavior. And again, if we apply more negative backgate voltage, the superconductivity becomes stronger and then get suppressed and finally disappeared if we keep applying more negative backgate voltage. So basically, from this series of data, we can extract the critical field as a function of backgate voltage. And the data looks like this, and we can see two superconducting domes, one for the 001 direction and the other for the 1-10 direction. And also we can see the dome shifts for the two domes have a shift, which means the backgate voltage for the maximum upper critical field has a 0.2 volts difference. So this is interesting, and we are seeking for the possible explanations. Probably this is related to the Lifshitz transition in the LaAlO3 interface. In Anani's paper, they studied the Lifshitz transition in the 001 LaAlO3 interface. Basically, Lifshitz transition means new bands of a different symmetry are populated when the carrier density above a critical value, because the band structure of the 001 LaAlO3 interface looks like this. The DXY band is the lowest band, so when the carrier density is low, only the DXY band is populated. But above a certain critical value, the higher band, the hybridized DXA-DYZ band is also populated. So the transport shifts from a one-band model to a two-band model. And this transition is related to the superconductivity, as reported in the Nature Communication paper. The maximum critical temperature sits on the critical density value, which is similar in our case. Here we are plotting the upper critical field as a function of backgate voltage. But we are studying the 110-oriented LaAlO3 interface. The band structure can be different, like in this PIL paper calculated. For the 110-oriented LaAlO3 interface, the DXA-DYZ band is the lowest band, but the DXY band is the lowest band for the 001 interface. And also, we are studying the quasi-1D nanowires along two different directions. So probably the band structure for the nanowires along different directions is also anisotropic, and also there can be a different critical density for the Lifshitz transition. This may explain why there is a domain shift, superconductivity domain shift we observed. So as a summary, we have observed the anisotropic superconductivity of the nanowires at the 1-oriented LaAlO3 interface. And also we see the superconductivity domain shifts, and we think this can be related to the Lifshitz transition in the 110 LaAlO3 interface.